So let's look at this. Two charges. You can assume that they're the same or not. It won't change the answer. And you're going to move, in one case, move a proton between I and F, location, initial location, and the final location. And let's see what happens to the change in the potential energy of the system when you go from I to F. First for a proton, and then we'll look at the case for an electron. So start with a proton. Okay, so 50% for 1 and 33 for 3. For answer A, and 33% for answer C. So you know for sure that it's not 0. Okay? So let's go with the majority. Let's see. The change in potential energy bigger than 0. So what's the initial potential energy? Well, it's going to be given by the term, whatever this charge Q1 is, and Q2, and the proton's charge. So it's going to be like K, Q1 times the charge of a proton, which is E, divided by that distance, plus the other term, which is the K, Q2, the proton, and the distance to the proton. Let's say that we're midway, halfway between them. That is the interaction, potential energy of the interaction between the proton and 1, the proton and 2. There is a term missing here, which is the interaction energy between 1 and 2, right? But that's not changing just because I moved the proton. That remains the same, right? So I can just ignore that because I'm looking at the change in potential energy of the system. So what's going to change is how do these terms change as I move from I to F. Okay? So at location I have these R's, whatever they are. When I move to F, what happens to the corresponding R's, which I'm going to write it between the proton and charge 1, and this is the R between the proton and charge 2. What happened to both of those distances? They increase, therefore the potential energy decrease. So the final potential energy should be less than the initial potential energy. If the final is less than the initial, then your potential energy decreased. Think about what I said before, that you didn't, many times you don't have to look at the equation, just think about whether it makes sense or not. If you think of the rule that a particle left to itself would move from high potential energy to low potential energy, right? What would you expect? If you put a proton in between these two charges, what's going to happen to the proton? If you just put it not exactly at the line that connects the two, but just a little above that, there will be a force pushing that electron away, right? Because the electric field of 1 and 2, if you're not right at the middle point but a little above, points up, right? So that proton will be pushed in that direction, right? So the proton's motion will be always from high potential to low potential energy, potential energy. All right? So that tells you that the final potential energy should be less than the initial potential energy, because that's the direction in which the proton will move by itself. Okay? What about a positive charge here and a negative charge? And we do the same thing. Oh, by the way, for an electron, let me go back. You would expect the answer to be what? If instead of a proton, it's an electron. When moving from I to F, is still the change in potential energy negative? For an electron, the electric potential energy is bigger at the initial location or at the final location? Remember that the electric potential energy of the electron in that configuration, associated with the interaction with 1 and 2, will be negative, right? It would have a negative sign, because the two charges are different, the electron and the Q1 and Q2. So if that's a negative number, right, that negative number, as you move away, as the distance is growing, that negative number is getting, in magnitude, is getting smaller. That means it's growing, right? A large negative number is smaller than a small negative number, right? So that means that the potential energy is growing in that case. So for a proton, this will be the answer. For an electron, this will be the answer. Again, you can think about it in terms of the natural motion of the electron when placed at that location. The electron would move, if you place it at F, it would move towards I, because it will be attracted. If it's an electron, it will be attracted by the two positive charges. It will be pulled down. So that means that the potential energy of the electron at F should be bigger than the potential energy of the electron at location I. Right? So the final is bigger than the initial, therefore delta U is bigger than 0 for an electron. So watch out for the sign of the charge. Okay. So what if I move now the charge from initial location, start with the proton, to the final, but now the charges are one plus and the other one's negative. So let's say that this is plus Q and this one's minus Q. And again, the options are delta U bigger than 0, delta U smaller than 0, C, delta U equal to 0. And we're doing proton again. The first case is proton. 50% chose 3. And that's the right answer. The potential energy at the initial location is the same as the potential energy at the final location, only because both of them are 0. Right? If the two charges have equal magnitude, then the potential energy associated with the interaction between the proton and each one of the charges is this, plus the other term, which is minus K. Q was negative, right? The charge of the proton divided by R. So this is equal to 0. Right? If the initial point is right between the two charges, then it should be 0. And if you are at the final location, then whatever your final location distance is, it will be the same for both of them. Let's put that Ri. And the two terms will cancel each other. Okay? So the difference is 0. Notice that this is associated with the fact that for a dipole, which is what you have there, the electric field along the line that bisects the dipole, the electric field points this way. So if you move a particle, whatever the charge of that particle might be, along a line, along this line, then you would be moving the particle along the path that is perpendicular to the force acting on the particle. So you are not changing the energy of that particle. Therefore, the potential energy should not change. Okay?